break, I did ask Ben whether there was an easier way to make a living than configuration spaces. I'm happy I have one. But anyway, these are fascinating talks, and welcome back, Ben. Please, thank you.
Thanks, Tony. Yeah, so what I'd like to do now is try to get at some calculations, or something in that direction at least, to compare with what we said about configuration spaces in Euclidean space. And so this complex is very good for calculations. So let me just show you an easy calculation you can do, which doesn't actually illustrate how good it is at calculations, but okay, it's a calculation. So an immediate corollary is if we're looking at a star graph of any valence, then the homology of the configuration spaces of that star graph, it vanishes in degree greater than 1. So there's only H0 and H1. H0 is just Z because the space is connected. And we can say exactly what the rank of H1 is. In fact, we can say it's free. So H1 of the configuration space of K particles in the star graph of valence N is free of rank this number, n minus 1 times k plus n minus 2, choose n minus 1, minus k plus n minus 1, choose n minus 1, plus 1. Why is this a corollary? It's a corollary because if we inspect the complex, this has only one vertex of valence not equal to 1. At a vertex of valence 1, there are no differences of half edges because there's only one half edge. And so the complex is 0 above homological degree 1 because the only pieces of the complex that have positive homological degree are the half edge differences. So there's just no complex above degree 1. How do we calculate the rank of H1? Well, the Euler characteristic is easy to calculate from the complex, from the combinatorics of the graph. And using the Euler characteristic, this just falls out. So one thing to notice about this, does anybody notice anything about this as a function of K? What kind of function of K is this? It's a polynomial function. It's a polynomial of what degree? It's a polynomial. What degree does this polynomial definitely not have? 0. It doesn't have degree 0. It's a polynomial of positive degree. Okay. So in particular, homological stability fails for graphs. In fact, it failed as soon as we stepped like a single foot outside of the world of manifolds. Immediately it failed. Okay. So we should think that probably homological stability doesn't hold very often for graphs. Okay. Is there a question?
Minor thing. I want to make sure that the H sub I B, is that supposed to be B sub K at the very first one?
It actually doesn't matter.
It doesn't matter. Okay.
Because it's true for all K. So.
Oh, that makes sense. Okay, great.
I asked that.
But good question. Other questions?
Sorry.
But it is still a polynomial. And when we were thinking about stability phenomena yesterday, what we said was that homological stability, constant growth, is a particular case of polynomial growth, polynomial of degree 0. And that came from a polynomial ring with one generator using Hilbert structure theory. This is a polynomial. And so all hope is not lost. There could still be some kind of structured asymptotic thing happening along those lines, right? And the other clue is that if we look at the form of the Sviatkovsky complex, this just came to us combinatorially. We don't really have a reason to think it's a thing, but we do have this factor of a polynomial ring generated by the edges out front. And if we think about the differential for a second, what we'll see is that, in fact, this is a differential graded module over this polynomial ring. So that seems like a relevant thing, but it would be good to have a topological source for that structure, right? So here is the topological source for that structure. So it's called edge stabilization. So if we're going to have a topological source for the action of this polynomial ring, what do we actually need? Well, to have an action of the polynomial ring generated by some set, you need a bunch of maps, one for each set, one for each element of the set, excuse me. And you need those maps to commute with each other, at least at the level of homology. If you have that, then you will get an action of the polynomial ring generated by those maps. By maps, I mean endomorphisms of some object. That's important, of course. So what I need to do to produce an action of this ring is hand you a map, an endomorphism, one for each edge. Okay, so oh, sure. So given an edge of the graph, what we need is a stabilization map, which I'll call sigma E, from the configuration space of k particles in the graph to the configuration space of k+1 particles in the graph. And then if we combine those together, we will obtain an endomorphism, which is just the induced homomorphism of the total thing. Okay. Okay. How do we do it? Here's how we do it. Here's a picture of the edge. There's like a local picture of the edge. There's lots of graph that happens outside of this picture. And there are some number of particles sitting on the edge, a sub configuration. So there's maybe a particle at the endpoint, and there's another particle here. Okay. And so what we are going to do is we're going to replace this subconfiguration on the edge. The edge is parameterized like from 0 to 1 maybe, with the collection of averages of consecutive particles and endpoints. So what does that mean? It means that I go from left to right and I average consecutive things that I see. So this one's at the vertex, and I average it and the vertex, and I get the same thing. So there's a particle there still. Now I see this particle and this particle. If I average them, I get that. And I put a particle there. Next, I see this particle and this endpoint. And if I average them, I put a particle here. Okay. And by doing this, what we do is we increase the number of particles on that edge by 1 every time. And outside of this local picture of the graph, we leave all particles stationary. And you can check that this is continuous, essentially because when a particle is at the endpoint, we average it with the endpoint, it doesn't move. So that preserves continuity. And this is the yes. So this is the description of this stabilization map indexed by this edge. But because we are doing nothing to the particles outside of this edge, the different stabilization maps commute with each other, and so do produce an action of the polynomial ring. Yeah.
What if we have a point at the other vertex of H?
That's fine. If we have one here, then we also have to average that particle and that endpoint, and then we have a particle there.
Okay, thank you.
Yeah. Other questions?
Would anyone online like to ask a question?
So you can only, how do you choose which point to average? Like if you have like maybe like 3 points in the center, how do you choose which one to average?
We
with the
average
endpoint?
consecutive pairs. So we have to we have to
I
like
see,
choose
I
a
see.
parameterization of the edge by 0, 1, but the choice doesn't matter up to homotopy. And then we're averaging only consecutive pairs.
Okay, I
Yeah.
see, I see.
Other questions? Okay, and so then the theorem that I proved with my collaborators, or rather, this is the sort of theorem that you notice. It doesn't actually take all that much to prove. Is that the module over this polynomial ring, which is acting topologically by edge stabilization, given by the homology of the configuration spaces of graph, any graph, is finitely generated. And the proof is as simple as could be. You have to think for a second about does this topological action actually coincide with the algebraic one you observe at the level of the complex? But of course it does. And once you establish that, then we run the same argument that we used yesterday, except less sophisticated. We say, look, that's finitely generated, and that's a subquotient. And the polynomial ring is Noetherian. A couple of comments about what does and doesn't generalize to the ordered case, or really more comments about what doesn't generalize to the ordered case. As I said before, this complex is totally fine for the ordered case. You make a few changes that are obvious. This absolutely does not work because none of these particles are the same as any of these particles, right? We replace the entire subconfiguration with a new subconfiguration. And so if these had orderings, or rather, if these had labels that were part of a larger labeling scheme, it would be entirely impossible to decide in a consistent way how to label these particles, because we're not adding a new particle, right? We are changing the subconfiguration entirely. So this construction doesn't work for ordered configurations. And the reason that it does work for unordered configuration spaces is that the configuration space of the interval, configuration spaces of the interval are all contractible, as we saw before. And so the obstruction problem of producing this map is trivial. But the ordered configuration space is a disjoint union of a bunch of contractible components, and that multiplicity of pi 0 obstructs the possibility of producing a map like this. Okay, there's something that you can do, which is like this, but more complicated and produces more maps for the ordered case. And then you have a different problem. You have a big twisted algebra in the sense that we talked about yesterday acting in the ordered case, and it's not Noetherian. And then you just can't do anything. Or you can't do anything, obviously.
What if you impose an orientation on a graph, and then you would be able to order the new particles? Like, for example, you think of those three particles, they move along the orientation, and the new one is the.
So it's perfectly possible to order these particles,
Mhm.
but these particles are taking part of an ordering on all of the particles in the whole graph, not just on this edge. This is a subconfiguration. And that really is the issue, because like this particle can now leave and go hang out in the rest of the graph, and then its label can't be messed with, right? So it's not really an ordering of just these particles, it's the full
Okay.
ordering. Yeah.
Thank you.
Okay, so so the ordered situation is significantly more complicated, and I won't really say anything about it today. Suffice it to say that some current work that is almost finished being written up with Louis, who's right there, and Nick Babrikoff, who's not here, proves some of the same theorems that I'm about to state, or proves analogs of some of the same theorems that I'm about to state for ordered configuration spaces of graphs without using Noetherianity. So that's somewhat surprising in this business of stability phenomena. We sort of are able to prove many of the things that one would want to prove without having to invoke Noetherianity, which is usually the key.
Repeat again, how in the proof of this theorem you're using this map here, just briefly.
Oh, yeah. So in saying the ZE module, this is how the action arises. Yes. Other questions? I have said so many things over the past 5 hours and 12 minutes that it's hard to keep track even for me. Okay. So the obvious question that one asks oneself knowing this is, well, we have a finitely generated, again, I should say finitely generated H degree. So if I fix the homological degree, I have a finitely generated module over a polynomial ring. And so eventually it's the Betti numbers over whatever field I want are calculated by the Hilbert polynomial of that module. And so the question is, what can we say about the Hilbert polynomial? So, what can we say about the Hilbert polynomial? Or in other words, what can we say about the Betti numbers for K large? Do I want to try to put this on this board at the bottom? Sure. So I'm going to give you a theorem about the Hilbert polynomial right now. In order to do that, I need a piece of notation, which is a graph invariant, the definition of a graph invariant. So the graph invariant is called delta. It's an invariant of the graph gamma, and it comes in a countable family, one for every natural number. I, you should think of as being the homological degree. It's going to be connected to the homological degree. So here's what you do to calculate delta. You look at sets of essential vertices of size I. So if I'm looking at trying to calculate delta 2, I look at pairs of essential vertices and I remove them from the graph. Okay, so I look at graph minus a subset of essential vertices of size I. And in doing so, if I had a connected graph, maybe I don't have a connected graph anymore because I took out some vertices. And so I can look at how many connected components there are. And I can look at the largest number of connected components that I can get by removing that many essential vertices. Okay, so again, if I'm trying to calculate delta 3, I look at all triples of essential vertices in the graph. I remove them, I count connected components, and delta 3 is the largest number of connected components that I get that way. So W ranges over subsets of essential vertices. Are there any questions about the? Oh. Questions about the definition? Is it clear?
If I is bigger than the number of essential vertices, then you just take it to be 0.
I think the good convention is maybe to take it to be minus infinity.
Okay, I see. Thank you.
Or maybe -1. I can't remember. In any case, negative. Negative. Yeah. Other questions? Okay. So the theorem that connects this number to the Hilbert polynomial is the following. So so fix a connected graph, or fix a field, and a degree of homology that you'd like to know about. And for simplicity, let's take the degree of homology to be bigger than 1. That's not actually a restriction, but the statement is slightly simpler. In any case, H1 is completely understood by work of Cohen Park. So, and then let's look at a graph that's connected. That's also not really a restriction, but it is just for simplicity. And let's say that that graph is not a manifold, so it does have an essential vertex. Then what we can say is that the homology in degree I of the configuration spaces of the graph with coefficients in that field is eventually equal to a polynomial. That much follows from that theorem. Polynomial in K. And the degree of that polynomial is exactly this number delta, -1. So that's the degree of the Hilbert polynomial. And we can also say what the leading coefficient of the Hilbert polynomial is. And it has 2 pieces. So one piece also has to do with delta, which is 1 over delta -1 factorial. And then there is a contribution for every, so remember, to calculate this delta, we look at sets of essential vertices of size I, and some of them maximize the number of connected components after removal. Those are the ones that sort of realize delta. And so there's a contribution to the leading coefficient for every one of those maximizing subsets of essential vertices. So I have to take a sum over W of size I such that, well, I'll write that in text. Sum over W. And then for every such set of essential vertices, I take a product over the vertices in the subset of the degree or valence of the vertex minus 2. That's the leading coefficient. You seem disturbed.
We have problems if it's a finite field of order P and if K is P. Is that a problem?
Yeah. Oh, I think the objection is, wait a second, this is probably not an integer. Is that the objection? Oh, no. So this is a polynomial. The polynomial is like with coefficients in the rationals. And it's calculating the dimension of the homology. So the polynomial does not have FP coefficients. Yeah. It's just a polynomial that calculates the number. Yeah. If anybody was worried that this is not an integer, that's okay because it's just the leading term of the polynomial. Polynomial has to be an integer valued polynomial, but the leading coefficient can certainly be rational. Other questions? Yes. Oh, I was going to write that. Sorry. So W ranges over subsets with number of connected components equal to gamma is an edge K. What happens if you can work that out. It has no essential vertices. So the answer is going to be pretty simple. Yeah. And that space, the answer will be 0. The answer will be 0. It's a fancy way of writing 0. Other questions? What? Oh, if I is equal to 1, then there's a dichotomy between when delta is equal to 1 and when delta is not equal to 1. So something that can happen is like this graph. Delta 1 of this graph is 1 because if I remove an essential vertex, it's still connected. And that somehow is a pathological example. And so if we assume by fiat that delta 1 is greater than 1, then exactly that statement still holds for I equals 1. And then otherwise, there are some like special cases that you have to deal with like sort of by hand. And that has been done. That was done before our work. Yeah. Sorry? I'm sorry. Oh, well, it's known. There's definitely a formula. I don't, do I know it off the top of my head? I guess I would have to think about it. Yeah. So it's not that there's not a formula, it's that I don't know it and I didn't come up with it. So. Oh, the question, yes, sorry. The question was asking about the restriction I greater than 1. So it was asking when I equals 1, what happens? And the answer was that if delta of the graph, delta 1 of the graph is also greater than 1, then the statement of the theorem is true for I equals 1 without any change. But pathological examples like this, where delta 1 is equal to 1, have to be dealt with differently. Other questions? Okay. So I'd like to talk toward this theorem a little bit with the rest of the time. I don't know if we're going to see much of a proof. We'll see how far I get. But at the very least, I owe you an explanation of where that number delta comes from. So, so the question is why delta? Okay. Okay. Specifically, why degree delta? And okay, one way to think about it is if you want to calculate the degree, then you could bound the degree from above and below and show that they are the same bound. If you wanted to bound the degree from below, then your task is maybe somewhat easier because all you have to do is produce homology classes. Just generate a bunch of homology classes and show that the submodule they generate grows of that degree. Okay. So that's what we're going to do. In order to bound the degree from below, we're going to produce a bunch of homology classes and show that it has that degree of growth. Already on board? Or rather, we're not going to show it, but we're at least going to see what the classes are. So the idea is actually one of the first ideas from today. So if we have an essential vertex in the graph, somehow this is all about these essential vertices and what are they doing? If we have an essential vertex, then we have valence at least 3. We can produce an embedding from a star graph with 3 edges into our larger graph at that vertex. Okay, so and we have to make choices to do that, but that's okay. So if we have an essential vertex, then we have an embedding. I guess I have notation, so I have to draw pictures. We have an embedding of S3 into gamma. Okay, and so what that produces is a map at the level of configuration spaces. And we know that the configuration space of 2 particles here is a circle. And so we can take that homology class and we can push it forward into our larger graph. Okay, and that produces a star class, what we call a star class in homology. In H1 of the configuration space of 2 particles in gamma. Is anybody not 1000% sure what we are saying here? Yes. Yes. Yeah. So, so the question was, do we have to choose 3 edges at that vertex? And the answer is yes, absolutely. There are many star classes at each essential vertex. Yeah. Great. I'm glad. I'm glad we did. I don't remember doing that, but if we have a set of essential vertices, W, well, that leads to an embedding of a disjoint union of W many stars into the graph, 1 at each of those vertices. And then configuration spaces take this disjoint union to a product, or if we say it in more pedestrian terms, this star class is when 2 particles orbit each other by taking turns passing through the essential vertex. And I can just have two particles do that at each of the essential vertices in my set, right? So I can have two particles orbiting each other over here, two particles orbiting each other over here. They don't crash into each other, so I stay in the configuration space, no problem. And so that means I have a circle's worth of parameter for each of my vertices. So I have a torus. So this produces what I'll call, or what we call a W torus, W being the set of vertices in degree size of the set of essential vertices, because there's a circle factor for each vertex, and cardinality 2 times the number of essential vertices, because there are 2 particles needed at each vertex to do that. Okay, so this is a construction of a kind of homology class in the configuration space. That's what this is. It's called, it's a torus. And the observation is that so once I have this homology class with these homology classes, I can hit them with the polynomial ring that's acting, right? So if I have an element in the module, I can act with the ring and generate a submodule. And the observation is that the action of the polynomial ring on the edges on one of these toric classes factors through the quotient map of rings, where I take the set of edges and I identify them if they're in the same component of the complement of W. So I can identify edges together and end up with the polynomial ring generated by the connected components of the complement of W. So why is that? Well, let's think about it. Let's look at an example. So if I have this graph, the theta graph, then my star class, which is an example of one of these toric classes, alpha, is where 2 particles orbit each other by taking turns passing through that vertex. Now I'm going to start multiplying by polynomials in the edges. There are 3 edges, 1, 2, and 3. So this is edge 1, edge 2, and edge 3. And so I can think about what E1 times alpha is. E1 times alpha is represented by this configuration, where I have 2 particles orbiting each other over here and 1 particle stationary on edge number 1. E2 of alpha, similarly, would be this configuration, right? And obviously, there is a homotopy between these 2, because there is no traffic obstructing this vertex. I can move this particle onto that edge at will, no problem. So that tells us that E1 alpha is equal to E2 alpha, and for the same reason, that's equal to E3 alpha. Okay, so as long as I can find a path of edges in the complement of the set of vertices connecting 2 edges, they act the same. And that explains why the action factors through this quotient. Okay. So that means that the submodule generated by a W torus exhibits growth of degree at most the number of connecting components minus 1. So why do we get that much growth? The theorem says that we have some homology that grows as fast as delta minus 1. Indeed, you have reason to worry that there might be further factorization. Like, basically, the question is, like, is the submodule generated by alpha, by one of these toric classes, free over this quotient? If it was free over this quotient, then it would have exactly the degree of growth that we want, namely number of connected components minus 1. Okay, well, is it free over the quotient? Sometimes no. So if we look at another example, if we give the theta graph a tail, I guess I wanted to put an intermediate example before I went there. So in this graph, there are two choices of this alpha, right? There's one on this side, and there's one on the other side. Right? It turns out, and you can calculate this using the Sviakovsky complex that I wrote down before. Is there a question over here? That's fine.
What happens if two of those S3s intersect? I mean,
Yeah.
Essential vertex. But what if you had an essential vertex below that, and it shared two of the edges, and there were particles?
Yeah, that's a good question. So,
how do you separate the cohomology calculation in that case?
yeah, so this is all like topological and not combinatorial. And so, if you want to think about it combinatorially, what I would say is that you are entitled to subdivide the graph arbitrarily before you make the embedding. So I can subdivide the graph by putting bivalent vertices here, or I guess maybe I'll use the other picture, or maybe I'll break off onto the side. I think what you're worried about is I cannot both make an embedding here and an embedding here. I can't make any embedding actually of the star graph, strictly speaking, into this graph, a combinatorial embedding. And the answer is, well, put bivalent vertices here. That doesn't change the configuration space because it's topological invariant. And now I have disjoint embeddings of the star graphs.
What if you draw another curved edge down the bottom, another different curved edge right there, and now put another particle on that bottom edge? See, you've got that essential vertex on the left. Yeah, but it's essential in two different ways. Well, a lot of different ways, but at least in two different ways.
Right. So when we I'm not 100% sure that I understand your question, but when we do this business of constructing the torus, what we do is we choose the collection of essential vertices. So I might choose like these two. And then for each of those essential vertices, we choose 3 edges at it. So like maybe for this one, I'm going to choose these 3. Maybe for this one, I'm going to choose these 3. No problem. And then with that data, we get a homology class. And if I made a different choice, if I chose these 3 edges instead of those 3 edges, I would get a different homology class. I'm not allowed to do this move and this move at the same time. That's not allowed.
I see. So you're saying that it will produce a different homology class when it's considered separately?
Yes.
The fact that they sort of intersect in this sense, that has no effect on those homology classes.
So effectively, what this number is measuring is those choices. So this number and the delta up here are like coming from this ring, the asymptotics of this ring, and the rest of this leading coefficient is measuring those choices that we are allowed to make. Yeah. Yeah, you're welcome. Other questions?
when you say like dB minus to measure the choices, I'm wondering why the choices isn't given by like dB choose 3, but
Yeah.
it's -2.
Great question. So you would think that. There are actually, so there are two relations that reduce degree choose 3 to degree -2. One of them is sort of an obvious inclusion-exclusion relation, which you would come up with if you thought of it for 30 seconds. Like all of the different choices are not linearly independent because you can think about it. There's one obvious relation among the different star classes. And then there's a less obvious relation after stabilization. So there's a relation that's like, well, we can talk about it after. It comes from, both of the relations I'm talking about come from 4-star. And basically it's like, if I take the star class with those 3 edges and multiply by that edge, plus the star class with those 3 edges and multiply by that edge, and so forth, and I add up all 4, I get 0. And so somehow, even though that's not a relation on generators of the module, asymptotically it acts like a relation on generators of the module. So those two relations cut down the, like asymptotically somehow you can always assume that your 2 favorite edges are involved in making the star, and then the remainder of your choices are dB minus 2. Yeah. These are good questions. Are there any other questions? Okay, so what I was going to say is that in this graph, there are 2 choices of the star class, and an easy calculation that you can do with the Sviatosti complex shows that, in fact, those 2 are equal. And to get back to your question, I don't remember your name, and you're not, what's your name? Georgia. This sort of explains why I equals 1 is pathological. This class being equal to this class is the problem. This is called, we call this the theta relation. And what it means is, if we look at a third example, I can add a tail to my theta graph. And look at, as we did up here, the star class that involves these 3 edges. Then for the same reason as before, we have E1 alpha is equal to E2 alpha is equal to E3 alpha, exactly as above. But then because of the theta relation, we're able to move this class over to this vertex. And if we multiply by, sorry, I don't need to label it. That's the 4th edge. If we multiply by the 4th edge, there's now a path disjoint from this vertex that connects that edge to the other 3 edges. And so that shows that, in fact, also multiplication by E4 is the same as multiplication by E1 through E3. And that's a larger quotient. Imposing the relations that all the edges are equal is a larger quotient than you should have if you just expect to remove this vertex and only have relations corresponding to connected components. Because if I remove this vertex, I have 2 connected components, 1, 2, and 3, and 4 separately. So this relation shows that sometimes the action of the polynomial ring factors further than this predictable quotient that we somehow want. So sometimes it factors further. Due to this relation.
What does the word eventually mean?
For a sufficiently large K. For a sufficiently large K. Yeah. If you ask me what sufficiently means, I don't know. Yeah, we don't know what the stable range is. It's probably not so hard to calculate. It's just exactly, yeah. And so what we prove, what this example shows is that so let's back up for a second. What we wanted was for these toric classes to be producing growth as predicted by the theorem. And this seemed promising because this is the growth that we want. But then this relation makes us sad because it says, well, maybe they actually grow slower. Okay? And so what we prove is that if W, the set of vertices, if W maximizes the number of connecting components after removal, so in other words, if W realizes delta, then for some W torus, we have that the submodule of homology generated by alpha is actually isomorphic to the free module over this quotient ring as we would like. And so what that means for some alpha, for some W torus. And so what that means is that the rank of HI is at least the rank of the submodule generated by this particular class. And the asymptotics of this are exactly 1 over delta minus 1 factorial times k to the delta minus 1. That's an easy calculation that you can make. So this tells us that at least the degree of growth of the Hilbert polynomial must be no smaller than delta minus 1. Okay. So I think I want to go on, offer one perspective that also points to an open, interesting open direction in the field that this theorem raises, and then I think we'll call it for the day and for the week. And so that's the perspective of torsion. So one thing that nobody asked about, normally someone asked about this, is nobody pointed out or asked whether the characteristic of the field has any. You did. That's right. I just didn't understand what you were asking. So I take it back. Tony asked, and none of you did, but you should have. So a notable thing about the theorem is that the characteristic of the field plays no role. This number is independent of the characteristic. This number is independent of the characteristic. And that's maybe surprising. And so because sort of the difference between rational and mod P homology is something about torsion, this must have something to do with torsion. So so let me just say something about torsion. So there's a theorem of Coe and Park, which says that torsion in the homology of the configuration spaces detects planarity of the graph. So so there is torsion in H1, in fact, it is two torsion. If and only if the graph is non-planar. I think this is essentially the Van Kampen construction. We can actually see where that torsion comes from with what we know. So let's think about K5, which is one of the two non-planar graphs that I know. So that's K5. And let's look at one of these star classes in K5. So let's look at a star class at this vertex using these three edges. That one, and that one. I can extend this sort of small embedding of a star graph with three edges to an embedded subdivision of the theta graph that we've been talking about. So I can extend this to be one of the edges, and I can extend this to be another of the edges, and I can extend this to be the other, the third edge. Okay. Does everybody see that? And then if we contemplate the theta relation says star class on one end of the theta graph is equal to star class on the other end of the theta graph. But because the graph is non-planar, somehow the cyclic ordering of the edges has been reversed. And so actually, this star class is equal to the star class going the other way at that vertex, if you think about what the theta relation says in this case. And of course, there's no reason you have to stop there. You can then say that that's equal to the star class going this way at this vertex, and that way at that vertex, and that way and that way. And that tells you that this star class is equal to the star class going the other way at the same vertex. So, and if you think about degrees of the antipodal map, what this tells you is, or not the antipodal map, degrees of a reflection. What this tells you is that the star class alpha is equal to -1 times itself. And so that means that it's two torsion. So that's the two torsion that detects planarity, non-planarity. This example, this two torsion that detects non-planarity, is the only example of torsion in homology that is known. So this is the only torsion that's known. This is the only known torsion in homology. Just for graphs, And so there is a conjecture, which I don't think anyone has actually made, but somehow someone is aware of it as a conjecture. Do you believe this, Louis? Or you probably know what I'm going to say. Do you believe it? Okay. Maybe this is Louis' conjecture. No, I won't write it. Some folks conjecture that if gamma is planar, then the homology of its configuration spaces is torsion free. Do you believe that? You don't disbelieve it? Okay, that's a good start. Yeah. Is there a question?
Oh, two torsion.
Yeah.
Two torsion.
And maybe people also believe that any graph the homology is has no odd torsion. I have no opinion about these conjectures, except that they are not warranted by calculations, because not enough calculations have been done to warrant them in any way at all. You can for a little while, but it chokes out. Like that's, yeah. Oh, the question was, can you not just do this on a computer? And the connection to the theorem is, the theorem says that asymptotically the conjecture is true. So asymptotically the conjectures hold. In the sense that the dimension of the homology with Q coefficients has the same asymptotics as the dimension of the homology with FP coefficients. And if you had a space and you knew that the Betti numbers were independent of the field, reasonably nice space, then the universal coefficient theorem would tell you that its homology was torsion free. So this is somehow saying that asymptotically there's no torsion, which concretely means that any torsion that there is has to grow slowly under the action of this polynomial ring. The submodule of torsion grows slowly. And so it comes from some, if it's there, it comes from exotic weird classes that we don't understand. Yeah.
But does the point at which the dimension stabilizes depend on the characteristic?
That's a good question. I don't know the answer to that. Sorry, oh, you had the microphone, so they heard you. Yeah, I don't know the answer to that. Yeah, I don't know. So the last thing I'll say is a conjecture about torsion that I do believe that is more approachable. These conjectures, I think, are totally unapproachable, or like, I don't know. It's not clear how to approach them by the three of us who work on this. But here's a more approachable conjecture that is related and that connects to what we were talking about the previous days of the workshop. So if you have a planar graph, what can you do with it? You can embed it in the plane. Great. If you had a class in the cohomology of the configuration spaces of R2, that was torsion, and you embedded the graph into the plane, then you could restrict that cohomology class to the configuration spaces of the graph. And that would be a torsion class that might be 0 or might not be 0, right? So this is the only source, the only ready source of candidate torsion that we have. And so the conjecture is that the restriction of that class is 0 for any planar embedding of a graph. Okay, unless there are questions, I'm going to finish 23 seconds early.